We were working on this problem, the system of differential equations, and we got to the point where we were able to use the Laplace transform and solve for one of the variables after using some algebra. And now what we're going to do is we're going to go ahead and decompose this, take the inverse Laplace, and then perhaps solve for y. So we're going to go ahead and set this up. Now we have to be careful because what we have is something that we haven't seen yet, although we might have remembered it from Calc 2, is that when we break this up, we have a linear term, but then we have a repeated linear. And I don't think we've seen one of those yet in any of the video examples, so I'm going to show you how to take care of that repeated linear factor, just in case you don't remember from your Calculus 2 class what to do with that. So what we're going to do is we're just going to say that the decomposed fraction is going to be a over 3s plus b over s minus 1, not s minus 1 square, plus c over s minus 1 square. So you might remember, for a repeated linear factor, you have to have one separate fraction for each of the different powers in this case. Alright, so try to remember that just in case you might see that on an examination or on your assignment. Just like we've done in the past, what we're going to do is we're going to distribute the denominator and multiply through. So we get 1 minus 2s equals a times s minus 1 square plus b times s minus 1 times 3s. And then finally, we get plus 3s times c. And now we're just going to distribute everything. Let's rewrite the right-hand side as 0s squared minus 2s plus 1. And then we can go through and we can FOIL out everything on the right-hand side. And if we do that, we're going to get as squared minus 2as plus a plus 3bs squared minus 3bs, and then we have that 3sc. Alright, and hopefully we get a nice system out of this. It shouldn't be too bad. And so we match up the s squareds, and we get a plus 3b is equal to 0, so that's helpful. So we get a plus 3b is equal to 0. That takes care of our s squareds. We have an as, a bs, and a 3sc. And that's actually pretty good, because now what we're going to get is minus 2a minus 3b plus 3c is going to be equal to negative 2. And then finally, what's really nice is that immediately we just get a is equal to 1. Alright, so we like that a lot. That actually helps us out a great deal being able to solve these. Alright, so our a is equal to 1. And since a is equal to 1, and we can see that b is negative 1/3, since b equals a over 3, negative a over 3, which is going to be negative 1/3, so that's helpful. And then finally for c, we're just going to go through and we're going to solve this out, and we're going to end up with minus 2 times 1 minus 3 times negative 1/3 plus 3c equals negative 2. Good news is it's not going to be too difficult. I think it's going to end up being a 1/3 or negative 1/3. Now clearly we have a negative 2 on both sides. Those are going to cancel. This just turns into 1, so we're going to get 3c equals negative 1, or c equals minus 1/3. And so we can go ahead, we can substitute back all the way up here, and now we can start taking the inverse Laplace. Alright, so remember that a and c, or b and c are the same thing, and a is 1, so our Laplace of x is going to be equal to 1 over 3s, and then we had b over s minus 1, so b was negative 1/3, so that's going to be minus 1/3 over s minus 1, and then we got another minus 1/3, so minus 1/3 over s minus 1 squared. All right, and now we're going to take the inverse Laplace of that. All right, now fortunately for this one, the inverse Laplace is really easy, so we got really lucky with this one. So we take our inverse Laplace, so L minus 1 of L of x, that's going to be equal to 1/3 L minus 1 of 1 over s minus 1/3 inverse Laplace of 1 over s minus 1. We like that one. And then minus another 1/3 of the inverse Laplace of 1 over s minus 1 square. And that one's not too bad. All right, now fortunately, the first two of these are really easy, so let's just go ahead and hit those right away. Those we could just look right in the table. So x at t, so we have the inverse of the Laplace, that just turns into x, I'll call it x of t. Laplace inverse of 1 over s is 1. All right, we can look right at the table. So this becomes 1/3 of 1 minus 1/3. 1 over s minus 1 is really easy because that's just, we could either use the translation theorem or we could just look right in the table, and I think that that's going to be our e to the t power. That's really nice. And then finally this guy. All right. What we can do is we could just use the translation theorem on this. All right. So we could say L minus 1 of 1 over s as s approaches s minus 1. All right, and we can finally get to our answer. And so, or s, I'm sorry, 1 over s square. Right? And the good news is 1 over s square is one that's right in the table, and then we know what happens as s approaches s minus 1. That just becomes an e to the t by that first translation theorem. So mercifully, we get our x at t, and x at t is going to be 1/3 minus 1/3 e to the t minus 1/3. 1 over s square is just t, and then we have the e to the t. All right, so let's hold on to that. All right, so we're done with that. And now what we need to do is we need to solve for y. We could do this one of two ways. We could do this whole process of the Laplace transform again, or maybe we can go back to the original equation and we might get lucky that we can solve for y somehow because it's already in terms of x. And if we take a look at this equation, this first one, it looks like that we can get y prime in terms of x, which is really nice. Okay, so y prime is going to be equal to 1 minus x prime minus 3x. All right, so let's hold on to that. So y prime is going to be equal to 1 minus 3x minus x prime. Let me make sure I copied that down correctly. Yep. Okay, and we know what x is, so we can just substitute x right in there. We can get x prime very easily. So x prime is just going to be our derivative of this mess. So x prime derivative of 1/3 is just 0. Then minus 1/3 e to the t, which is really nice. And then we're going to have to use our product rule on this minus 1/3 t e to the t. So we're going to get a minus 1/3 e to the t minus 1/3 t e to the t. Or another way to set this up is that x prime is going to be minus 2/3 e to the t minus 1/3 t e to the t. All right, so I know it's not the nicest numbers in the world, but it is differential equations using Laplace transform, so we're probably not expected to get nice. All right, so we're going to substitute now, and we're going to be able to get y prime. So y prime is going to be equal to 1 minus 3 times the original x that we just got, which was 1/3 minus 1/3 e to the t minus 1/3 t e to the t. We kind of like that because all those 1/3s are going to cancel out with the 3. And then we also have to subtract out x prime. So that's going to be minus the quantity of our negative 2/3 e to the t minus 1/3 t e to the t. All right, so let's see what happens with this when we simplify it. Hopefully nothing too bad happens. So y prime, we're going to get a 1 minus 1. So that's going to cancel out with this, which is really nice. We have a negative 1/3, which is actually going to turn into a positive e to the t. So this is just going to be an e to the t minus a negative 2/3. So I believe we're going to get 5/3 e to the t. That's going to take care of these two terms. And then we're going to end up with a positive t e to the t and a 1/3 t e to the t positive. So we're going to end up with a 4/3 t e to the t. All right, and then finally what we can do is we can just integrate y prime to be able to solve for y at t. So we're going to integrate, and we're going to integrate with respect to t on the right hand side. This is going to be an integration by parts, so we're going to let u be equal to 4/3 t. We're going to let dv be equal to e to the t dt, and then du is our 4/3 dt, and v is just e to the t, which is really nice. All right, so let's see what we can get for y at t. So y at t is going to be 5/3 e to the t. uv is going to be 4/3 t e to the t minus the integral of v du, which is going to be the 4/3 e to the t dt. And we can't forget that there really is like that plus c in there. Now remember, we didn't need that before because we were just doing an initial value problem and the Laplace transform integrated all that into it. All right, but now we're just solving it using our standard integration method. We're going to get a negative 4/3 e to the t out of this, and we can just combine this with the 5/3 e to the t. So our y at t is going to be 1/3 e to the t plus 4/3 t e to the t plus, I'm just going to call this c1, might as well. Now remember, y at 0 is 0, so we're going to substitute 0 back in, so we get 0 is going to be equal to 1/3 e to the 0 plus 4/3 0 e to the 0 plus c1. That just goes to 0. This just becomes 1/3, so minus 1/3 is equal to c1. All right, and finally we get to our answer. We have that y at t is going to be equal to, remember we had our 1/3 e to the t plus 4/3 t e to the t, and then we have plus c1, which is really minus 1/3. And you might remember, it seems like a long time ago, but we did find x at t, and x at t all the way back up here. Here we can copy it just to be nice. So that way we have the solution all in one spot. Let's see if we can do some magic here instead of me having to fumble back and forth and copy it. Good enough. We're going to end up with 1/3 minus 1/3 e to the t minus 1/3 t e to the t. All right, so that's how we can utilize our Laplace transforms to be able to solve these systems. So a suggestion might be is that if you're solving these systems, the first thing you might do, try substitution. Second thing you might want to try is elimination. And I would just try those just in that order. And then as a last resort, try your Laplace transforms. All right. Full disclosure, there is another way to be able to solve these analytically. And another way to do this is by using matrices. All right, and you can use an eigenvalue and matrices. However, that might require a little bit of linear algebra background. And unfortunately, not everybody may have this as a prerequisite to the course. So that's why I'm only showing you the substitution, the elimination, and the Laplace methods. If you want to know the matrix methods, I would suggest going through and looking in the textbook. The textbook does lean heavily on those, but it does skip a lot of steps as it goes through.